Alright guys, we're going to start looking at our work examples by determining if the work in each case is positive or negative. Remember, if your force and displacement are the same direction, we have positive work. Opposite direction, we have negative work. So, part A, it says the road exerts a frictional force on a speeding car skidding to a stop. Here we have an example. We're slowing down. Now remember, that means our force is to the left. If we're moving to the right, our frictional force would be to the left. That means our displacement is actually going to be to the right. Those are opposite directions. So we have negative work. For B, it says a rope exerts a force on a bucket as it's raised up a well. We have this idea of a force pulling up, and it's actually moving up. Those are the same direction, so we would have positive work. C, air exerts a force on a parachute as the diver, parachutist, whatever, falls to earth. So the force of the air is up against the parachute. However, the displacement of the diver is down. Those are opposite directions, so we have negative work. So pretty simple. Okay, our first quantitative example. A tugboat pulls a ship with constant net horizontal force of 5 times 10 to the third. Guys, that's a fancy way of saying 5,000. And causes the ship to move through a harbor. How much work is done on the ship? So our force is 5 times 10 to the 3 newtons. And how much work is done on the ship? So our displacement is 3 kilometers. Now that is 3,000 meters. We have to make sure that we're using the correct SI units. So work equals F times delta X. So 5,000 times 3,000. We get 15 million, or, now that's joules, we can say, let's put that in scientific notation because there are a lot of zeros there, 1.5, oh, you can't see that, I'm sorry. 1.5 times 10 to the 7 joules. And that's the amount of work. Our second example. Here we have a weightlifter lifts a set of weights a vertical distance of 2 meters. We have a constant force of 350 newtons exerted on the weights, and it moves a distance. So delta x, or in this case of course it would be delta y, is 2 meters. What's the net work? Guys, again, pretty simple. Work equals force times displacement. These are in the same direction, so we have a positive work. 350 times 2, we get 700 joules. Remember, work is a transfer of energy, therefore it should come out to be joules. Okay, so another example. Let's look at this one first. Okay, we have a shopper in a supermarket pushes a car with a force of 35 newtons directed at an angle of 25 degrees downward from the horizon. Find the work done. Oh goodness, this is down. Should be done by the shopper on the car as the shopper moves along the 50-meter length of aisle. Nothing new here. Here's our cart. 25 degrees down. We have this situation. This is 25 degrees. You know, imagine when you push your cart, you're pushing down. This is 35 newtons. And we move this car a displacement of 50 meters. That's a long aisle. Again, work is the parallel force, or the force along our axis of motion times delta x. Well, here, this force is not along my axis, so I need to find this horizontal component. That's going to be 35 times the cosine of 25 times 50 meters. Let's do that. 35 cosine of 25 times 50. Okay, we get 1,586 joules of work done on our system. Pretty simple. In some cases, they'll want you to represent that as kilojoules. That would be 1.586 kilojoules. All right, last example. We have 2 joules of work is done in raising a 180-gram apple. How far is it lifted? Here we are given joules, so we're actually given the amount of work. So I'm going to write W equals 2 joules. Now this is a mass, so we got to figure out how does mass fit into our work equation. I'm going to go ahead and record that as kilograms. So 180 divided by 1,000 is 0.180 kilograms. And how far is it lifted? We're looking for delta X. Now, we know we're raising it and we know it's moving up, so our work is going to be positive, and there's no components here. There's no angle. So I just need to figure out how mass fits into the equation. If you raise something, you have to raise its weight. And we know that to find the weight of an object, it's going to be equal to mass times the acceleration due to gravity. So that's how mass is going to work in helping us find our force for this equation. So the mass is 0.18, gravity is 9.8. Now remember, it's only in kinematics when you have to use that negative 9.8. Here we use the positive 9.8 because it's just the value of g when we're talking about forces, because I've already drawn my arrow being up. So that's dealing with the direction already. Let's go ahead and figure this out. Work equals force times delta X. So 2 joules is going to equal this force, whatever that is. I'll go ahead and do that here. 0.18 times 9.8, 1.764 times delta X. Now to get delta X, we have to divide both sides by 1.764. And that will be my answer. Let's see. Delta X equals 2 divided by 1.764. That gives us 1.1 meters. Remember, the unit for delta X should be meters. Okay guys, well that's all of our examples. I hope you are kind of getting the hang of calculating how work works, or how we use work to transfer energy. More videos to come for energy, and we're going to start looking at energy pie charts.